Thanks for the organizers for this marvelous meeting and for inviting me here. I'll talk about some recent work on N=1 supersymmetry with a student, Jennifer Lin, who will also talk about this later today. And this is, of course, a period, the last 20 years, as we just heard, of a lot of progress in supersymmetric field theory. But as I'll try to indicate here, there are a lot of qualitative and quantitative phenomena that are really not understood, and there is a feeling that sort of the best is yet to come in this subject. Today I will talk about some specific example of what I just said, which is a generalization of N=1 SQCD, which has some mysterious ADE classification that we don't really understand. This is actually part of a development that has been going on for roughly the last 20 years, which is indicated in my outline. I thought the best way to do this is to describe some of the earlier work, because many issues in that earlier work are important for what we did recently and are not, I think, widely appreciated. So let me start with N=1 SQCD. That's another thing which Nati Zyberg sort of revolutionized more or less exactly 20 years ago. And what I want to say about it is summarized in this plot here. So this is, of course, an SUNC gauge theory with NF fundamentals. And the most important thing in this plot is actually the label of the axis. So of course, supersymmetric QCD, like most gauge theories, has a running gauge coupling, but this running gauge coupling is just there to confuse you. The way to think about all these theories is as labeled by a discrete parameter, this little x, which is basically like a discrete Hooft coupling that measures the strength of the gauge interactions in the infrared. And you can think of it as some analog of the N=4 super-Yang-Mills coupling lambda, or the discrete coupling of Chern-Simons theory. So everything that we say about the infrared limit of these theories is happening as a function of this parameter. And as a function of this parameter, there are a few regions in the plot, which I would like to remind you of very briefly. So if this coupling is small, the theory is basically like QED. It's not asymptotically free, and so it's free in the infrared. As this x increases, the gauge interactions at some point pass through the asymptotic freedom bound. The gauge coupling becomes non-trivial in the infrared, and as the coupling increases, the theory becomes more strongly coupled, by which I simply mean that the scaling dimensions of operators deviate more and more from their free values. Now, eventually, there is a phenomenon which we were familiar with since '94, that the description of the infrared dynamics in terms of the original degrees of freedom breaks down. So this is this region here, and we have to do something different if we want to understand what's going on. And this something different is use Zyberg duality, which is the statement that this original theory is equivalent to a different one with a different rank gauge group, some quarks in similar representations to the original ones, and importantly, a magnetic meson field, which is a singlet under the gauge group and sort of represents in the dual theory some gauge invariant combinations of the original quarks. And there is a superpotential like that. Now, this is a strong weak coupling duality, as you can easily see from this little exercise. As the coupling in the electric theory increases, the magnetic one decreases. And in particular, as I just said, the magnetic description provides a good description of this bad region in the electric language. So that's what I would call the A1 example of this general series that I'm going to talk about today. It turns out that you can generalize this significantly by adding an adjoint superfield under the SUNC group. and turning on a polynomial superpotential for it. At first sight, it looks like this is not much of a generalization, because for k equals to 1, this is just a mass term, so there is no reason to include this x in the infrared theory. The one case where you would think it does something is k equal to 2, where this superpotential is classically marginal. The gauge interactions make it relevant anytime the gauge theory is asymptotically free. And then the interesting thing here is that when this k is larger than 2, and naively you would say that this superpotential shouldn't do anything because it's an irrelevant operator, actually gauge interactions reduce its dimension enough that it becomes relevant in the infrared. And this is true for all k if the coupling x is large enough. It's so important to include it that if the coupling is too large, you lose the supersymmetric vacuum. And that's an analog of the region NF smaller than NC for supersymmetric QCD. Much like in supersymmetric QCD, the strong coupling region is better described in terms of a dual theory, which has some other rank gauge group, a similar charged matter, and in this case, lots, k, more precisely, singlets that couple to the magnetic degrees of freedom in this way. And just like in the other case, the magnetic coupling becomes smaller as the electric one becomes larger. So a lot of the comments I made about the previous case before are valid here as well. Now, when these theories were first analyzed, it was recognized that it's useful to think about them in terms of kind of singularity theory. I don't have time to talk about it much, but especially if you ask the question, what happens when you deform the superpotential to a general polynomial of degree k plus 1, issues from singularity theory come up. And this was picked up by John Brody, who was at that time a brilliant graduate student here at Princeton, who asked what happens when you replace the A-series singularity with a D-series one. So he just did what you would naturally do, added another adjoint field, so there are 2 overall, wrote a superpotential like this, and he found a structure which is similar to the one found in the A-series, but with some important new elements. So the similar part, which I don't want to dwell on, is that while, again, naively you would think that you don't need to worry about theories in which this k is very large, it actually turns out that, like in the previous case, it actually is important to include these naively irrelevant terms in studying the infrared dynamics. There is, again, an upper bound on the coupling above which there's no supersymmetric vacuum, and he found a dual description in terms of some SU 3K and F minus NC theory with the same sort of charged matter content and singlet mesons like this. So I will actually come back to these singlet mesons of his in a moment. The important new elements which I actually didn't appreciate until recently are the following. First of all, these fields X and Y are matrices. Now, they were matrices already in the A-series discussion, but there you didn't have to worry about it too much, because in the infrared, you could diagonalize the matrices and study the dynamics of the eigenvalues, which is basically what was done in the original work on the A-series. In the D-series, we have 2 of those things, and you cannot actually diagonalize them at the same time. So if you ask questions like what happens when you deform this to a more general polynomial with the same asymptotic structure at infinity, you have to deal with the non-abelian structure. And this leads to difficulties that will eventually get us stuck at some point in this discussion that are not understood to this day. What's the vacuum structure of these theories for generic deformations? The second important element that John introduced is certain quantum constraints on chiral operators. And since this is going to be important for me, I want to spend a moment on it. So if you look at the F-term conditions for the superpotential I wrote, they are x to the k equals y squared and the anti-commutator of x and y equal to 0. So if you asked, mesons are clearly important in Zyberg's work and generalizations. If you ask what kind of mesons are there, well, classically, you would form objects of this sort where the O's run over this set. And this looks similar to what Brody had, except that this index j for him had to run over 3 values. In other words, powers of y larger than 2 were not included, whereas the naive analysis that you would do here would give rise to any j, any power of y in these mesons. And so this looks at first sight incompatible with the duality that he advocated. Now, he was, of course, very aware of this, and he pointed out that when k is odd, it's actually okay, because by some simple manipulation, you can show that y cubed is 0 as a chiral operator classically. But for even k, this is not true. Well, the minus signs here, which are due to the anti-commutator structure, disappear. Y cubed is not equal to 0 as a classical operator. And so you have to take one of two attitudes. Either the duality he advocated is not true for even k, or the attitude that he actually took is that the constraint that you needed must appear quantum mechanically, despite the fact that it's not present classically. The reason I think he took this point of view is that you could flow from odd to even k, obviously. You can add to a potential like this with odd k some lower order term with even k, and it doesn't seem like it would be consistent to have a situation in which something works for odd k but not for even k here. And this constraint is not understood to this very day, and in fact, it needs to appear in the simplest possible example of this, k equals to 2, when the theory actually can be studied at weak coupling all the way from the UV to the IR. So this is something that, again, we don't understand and will eventually get us into trouble later on in this talk. So the next step in this development came in 2003, where Ken Intriligator and Brian Wecht, after their famous work on A maximization, asked the question, what can you do if you take an SUNC gauge theory with fundamental and adjoint matter? What kind of fixed points can you get? And they found an answer that to me is pretty remarkable, which is that this is the full list of things that work. So there are these four first entries that are very interesting, but I will not discuss for lack of time today. But the last 5 look like some sort of ADE classification. But I want to stress that it arose in a way that is very different from any ADE that you've ever seen, probably. It did not come from any geometric or algebraic considerations. It came from thinking about things like the NSVZ beta functions, A maximization, dynamics of n=1 gauge theory. And so this, again, remains very mysterious and cries out for some kind of interpretation. But I will not be able to offer one today. The A and D theories, as I mentioned here, we've already talked about. So the goal of the rest of this talk is going to be to understand the exceptional cases. The only one we will be able to actually understand is the E7 one, so I will start with it. And so what I did here is write down, make a table of all the quantum numbers under the global and gauge symmetries of the fields. If you've ever looked at n=1 SQCD or anything like that, you've seen analogous tables. This is not very interesting. And basically, I'll just try to follow my nose and go through the same analysis I went through before. So there is this E7 superpotential. I can write down the F-term constraints, and I can ask what kind of classical meson field operators can I write using these constraints. So that's an elementary exercise, and the answer is written here, where this little n parameter runs over essentially all integers. Maybe it's truncated at something of order nc, but we don't care. Now, this answer, you can show, has to be wrong. If this was the full answer, you would violate unitarity. So there has to be some process whereby a similar thing that happened in the other cases must happen here. The original description of the theory must break down, and something else must replace it. So the natural way to proceed, given everything I just told you, is to assume that there is, again, some dual description and see what it is. So this is basically what you would write down just under that qualitative assumption. You would write down the fields that have the same sort of quantum numbers as in the electric theory. You would add some magnetic mesons. But this is nothing, that relies on nothing more than that qualitative assumption that a duality of the general sort we discussed before exists. In particular, the rank of the dual gauge group is free. The number of these magnetic mesons that I called alpha here is free. There are charges, which are the only interesting thing about them, that are parameterized by this little rj, are free. So I didn't really do anything other than make that one qualitative assumption. Now, the interesting thing is that some of these recent developments in supersymmetry we heard about in the last talk are actually very useful here to determine all of these parameters: the rank of the dual gauge group, the number of the mesons, their R charges. The way you do that, so the easiest is the rank of the dual gauge group. That just follows from some 't Hooft anomaly matching, and it has to be of this form. But at this point, most of the things you're interested in, which are this alpha, the number of meson fields, and their R charges, are kept free. We don't know anything about them. So Jennifer later today will explain how they can be determined. So I will not spend much time on it. The basic idea is that if you look at the superconformal indices of the electric and magnetic theories, which of course must coincide on general grounds, you can determine all these numbers. Now, these indices are in general some horrendous functions of the chemical potentials, but Dolan and Osborne showed that they simplify significantly in certain Veneziano limit. And when you calculate those simple forms of these indices in that limit, you find some relations of this general form, which I don't want to dwell on too much, where T is some chemical potential. But basically, where the left-hand side is a polynomial and the right-hand side is not necessarily one. And by demanding that such relations are valid, you get to determine both the number of the magnetic mesons and their R charges. So you find that the number of these mesons is 30. In other words, out of this giant list that we found classically, only 30 survive. And when you look at their quantum numbers, you find that they are obtained by taking the big original list and applying this sort of constraint to it. Now, this constraint doesn't have any kind of rationale in the classical theory. There's absolutely no reason to assume anything like this. But if you want this kind of duality to hold, you need to impose it. So at this point, it could, this whole exercise could well come crashing down. But what you're saying at this point is that there is a dual theory with gauge group SU30 and F minus NC. and a certain number of mesons, which you can write down explicitly. So there's a bunch of tests for this picture. First of all, you get indeed that there are precisely 30 mesons, and the list of their R charges, that's a non-trivial constraint, is such that you can write a magnetic superpotential for them. The most non-trivial constraint is that 't Hooft anomaly matching is satisfied. In principle, you should also check that for any NF and NC, the superconformal indices actually coincide, but that's really hard in all of these examples, including the A and the D series. And so this has not been done so far in any of these examples. And these unitarity violations that I alluded to before are resolved. Here. Now, so this is basically the story. And if I stopped here, you would probably think that it's clear that if you just do the E6 and E8 examples in the same way, it will work the same. But actually, it doesn't. And the superconformal index is, again, a very clean way to prove that it doesn't. You can show that under that qualitative assumption that was the only assumption I made for the E7 case, and then had all these tests on, it can't work this way for E6 and E8. But at the same time, you know, some story like what I told you must be valid. A, because of the unitarity violation and strong coupling. B, because at least the E6 theory you can flow to from the E7 theory by turning on a relevant operator. So there must be some story like this here, but we really don't know what it is. This is something that we don't understand. And by the way, you know, when I mentioned before that the non-abelian structure will eventually come back to haunt us, this is partly what I meant. If we understood how to deal with the vacuum structure of these models with two adjoints when you cannot diagonalize the matrices, at least the E6 exercise would be easy. We would just start from the dual pair for E7, turn on the, whatever it is, x to the 4 perturbation to the superpotential, analyze the vacuum structure, and there would be, say, in the electric theory, the vacuum at x equal to 0, and it has to correspond to something in the magnetic theory. But to do that requires understanding that thing that we have not actually understood. These constraints on the chiral ring are something that really is bothersome, especially since, as I mentioned, in some cases they appear at arbitrarily weak coupling. So it would be nice to derive them. So one of the things we try to do is to look at the superconformal index and see how these states are lifted. But it turns out that this problem is not very clean because there are a lot of operators that can pair up at the same order as these quantum constraints. So we really don't understand that. Yeah, this point I made already. I stressed the fact that some type of matrix singularity theory is important here, but we really don't understand how that works. And the final point is that ADE, as I mentioned before, appears here in a pretty weird way. It's a dynamical way that we would expect can be geometrized. You know, we are used to, in string theory, having situations where dynamics gets geometrized in string theory, and so this problem seems to be crying out for some type of embedding of into string theory so that it becomes a manifest property, just like, say, the Zeiburg-Witten curve that was mentioned here before becomes geometric when you embed the problem into M theory. Thank you.
Thank you, David. So it's time for the questions.
So I didn't understand something you said. You said that you have a new chiral ring relation that exists at small coupling,
Yeah.
but is not visible semi-classically?
Well, I didn't say that. So when I said that, so what I meant in practice is the following phenomenon. So if you look at this case, and you set k equals to 2, so 2 happens to be an even number, and classically, you would say that this is a marginal, there are two marginal couplings here, the coupling of x cubed and the coupling of xy squared. When you turn on gauge interactions, as you know, the anomalous dimensions of x and y are negative. And if you're close to the asymptotic freedom bound, there's Banks-Zaks here. So the infrared coupling is small, right? So the D2 theory, D4 theory, the k equals to 2 case, has the property that it has a weakly coupled fixed point when this parameter little x is close to the asymptotic freedom bound. Now, what John Brody is telling us is that this theory has a dual, and in that dual, you have to impose the relation y cubed equal to 0. This relation, as I mentioned here, is absent in the classical theory by this analysis, but it has to be present at the infrared fixed point of the D4 theory. So this is a more detailed version of what I said. Now, you should be able to prove that, you know, say q tilde y cubed q, this operator, is a D term at the weakly coupled infrared fixed point of this theory, despite the fact that it does not have this property in the UV theory. We don't have such a proof today.
Other questions? So can I ask you one question?
Yeah.
So did you check Brody's conjecture using index calculation?
Say it again?
Did you check Brody's case using index?
The what case?
Brody's.
Oh, so actually everything I said, so you know, I didn't bother saying that, but you know, if you didn't know about any of these old dualities, you could derive them in the same way as I said here for the E7 case. If you took any of these ADE, whatever cases, and just assumed this, made this qualitative assumption of such a duality being present by looking at the index in the Veneziano limit, you could derive the rank of the dual gauge group, you know, all the operators. So yes, of course, the answer to your question is yes, in that Veneziano limit. I mean, again, the whole thing is a disaster. You probably have seen some of these, you know, Spiridonov and Vartanov formulae, where you write some horrendous hypergeometric function for the electric theory, another one for the magnetic theory. They have to agree, but you have no idea why they do. So you can check the first few terms. Typically, they involve integrals over, you know, the Cartan-Seb algebra of the gauge group. So that, of course, has not been checked. In other words, the agreement of the full index, but that's true for all of these cases.
All right, so if there is no more question, okay, thank you.